start the recorder. We are now streaming, so that's good. And then the second thing is to start up LogicSim so that we can use LogicSim to help explain, what those components are and how to make use of those components. So the first one we're going to use is the RAM component. But instead of the ROM component. But instead of just using the ROM component, we'll make it kind of fancy. Okay, we'll make use of the ROM component so that we can display like a bunch of LEDs, and then we'll show some patterns. Okay, as a sequence. So that's what we're going to do. So we'll redo the same circuit that we talked about last time about a clocked circuit. That involves an adder. It involves a register. So we go to memory for register. And do you guys still remember what a register is? The really, really, really long name of a register is a edge-triggered, gated, resettable bunch of D flip-flops. Okay, that was the last portion of the D flip-flop discussion. Okay, so you look at a register, you just kind of look at it as a whole bunch of D flip-flops. So in the default has 8 bits. We are not going to deal with all 8 bits. We're going to use a 3-bit register. And then the adder is going to also only have 3 bits. There we go. And we want the adder to only increment, each time. So we'll go ahead and create a constant. We go to wiring to make a constant of 1. So that 1 is going to be carry in, or K0 in our terminology. One of the input is the output of the register. And then the output of the adder is going back to the input of the register. So that this way, once we have an addition, we are storing the +1, okay, whatever the register has +1 back into the register. The other input of the adder is just going to be 0. So we're going to go to constant again. This time we're going to create a 3-bit constant because it has to match the input port width of the adder. And we want it to be just 0, 0, 0. So in hexadecimal, it is just 0. All right, there we go. And the carry out doesn't really hook up to anything. We don't have a use of, basically this is K3 in our terminology. Reset is going to be 0. In other words, we don't want to reset the register. So that's going to hook up to a constant of 0. So we go to constant again. And this time we make a constant of 0. And we can make it face north, just so that things line up a little bit better, like that. Okay. And we also want this register to be always enabled. In other words, whenever there's a rising edge at the clock, it will update its content based on the D port. So it's always enabled. And then we use a clock pin to connect to the little the triangle here. That's basically the clock of the register. Okay, so I'm pretty sure I showed you this circuit before. It is a very simple circuit for a counter. And the purpose of a counter is what? Is to count. Okay, very good. So this is a counter that counts up. You can have a counter that counts down. So what do you think I need to do to make this a countdown timer? I mean countdown counter instead of a count up counter? I only have to change one thing. Make it a subtractor, exactly. So instead of adding 1 to make it count up, we turn this into a subtractor to make it count down. Okay, so there are reasons why we have count down counters as well as count up counters. So this is just counting up, and it's already working, by the way. So if you poke the wires, you will see the output of the register. Now the content of the register is already here, so we know the content of the register in bits would be 0, 0, 0. So if you poke this wire, which is the Q port, it shows you it is 0, 0, 0. Now the slash is separating the binary format from the base 10 signed interpretation of the bits. Okay? So in today's class, the base 10 signed interpretation is not going to be very useful. So we'll be focusing on the binary representation, which is to the left-hand side of the slash. So the 0 is already presented to the adder. The other 0 is also presented to the adder, which is this wire here. And there's a 1 here presented as K0. So we are adding 1 to the input. So the output, not very surprisingly, is 0, 0, 1. Okay? But how come the 0, 0, 1 is not updating the register yet? Because the register needs, what does it need other than, in addition to the enable line being a 1, in order to update? We need a clock to, well, what edge are we looking for? It's a rising edge, okay? It's a rising edge. You can turn a register to use a falling edge also, but by default, it is a rising edge. So this is why the register is not updating. But the moment we make a rising edge at the clock line, it will take whatever is at the input port, which is 0, 0, 1 already, and use that to update the content of the register. So when I clock up here, okay, you can see the register changes right away to 1, which is basically 0, 0, 1. So every time we have a rising edge, the register is going to increment by 1. Okay? So you look at this and go like, well, but this has nothing to do with ROM. Okay? So what I'll do next is to make use of a whole bunch of LEDs. So we go to input output, and then we just drag a whole bunch of LEDs out, okay? Or we can just replicate LEDs. Okay, we'll have 8 of these. Oops. Because now we can replicate the 4 in order to get to 8 LEDs. There we go. So now we have 8 LEDs. And by the way, the abbreviation LED stands for light emitting diode. Very good. Okay, good job. But nothing is driving the LED, so I'm going to have to, have a mechanism to drive the LED. So what I want to do here is to have a cycle of 8 frames, okay? Because the counter can count from 0 to 7, so there are 8 distinct frames that I can refer to. But each so-called frame is going to refer to a location in a ROM that is not here yet. So the ROM is going to dictate what pattern the LEDs will display. The counter here is only here to control, I'll be talking about a frame 0, I'll be talking about frame 1, and it will just automatically increment to the next frame. So is that clear what we're trying to do? Sort of? Okay. So now we'll go ahead and pick up a ROM component from memory. And we have to customize it a little bit. The address bit will be now going to 3. Now, what just happened? We just saw a whole bunch of content or locations go away. So the A port, which is what I just changed, the width of the A port, that is the number of bits of the A port. With only 3 bits at the A port, now the A port controls how many locations I can address. So with only 3 bits, how many locations do you think I can address? You can count what is on the screen, which is 8, right? And by default, it was 8. So with 8 bits, which was the default width of the address port, how many locations can I address in the ROM? With 3 bits, we can see there are 8. So what do you think with 8 bits, how many locations can I address? 2 to the power of 8, which is 256. Okay, very good. So the width of the A port controls how many locations we have inside a ROM module. What do you think the D port is going to do? If I change the width of the D port, what is that going to do? Sorry? It's the number of bits as the output, which is also going to be exactly the width of one location in the ROM. Okay, so I'll say that one more time. We can adjust the data bit width, okay? And what it is specifying is the bit width of each location in the ROM, which is also going to be the width of the D port, because every single bit of a location is going to be presented in parallel at the D port. Are we good so far? So bit 0 of a location is going to appear as bit 0 at the D port. Bit 1 of a location is going to be bit 1 at the D port, and so on. Okay? So that is going to be staying at 8. So we'll keep this as 8 because we have 8 LEDs here. So if you want to make something even more fancy, like if you want to make an 8 by 8 matrix of LEDs, then you will need 64. No, 8 by 8 is 256, so you need a ROM to have 256 bits per location, which is not possible because it only gives you options of up to, I think, 32 bits per location. So if you scroll all the way down, it's only up to 32 bits. But right now, we'll just kind of stay at 8-bit here. All right. So the only way to hook up this, which is an 8-bit wire, to something like this, which is a 1-bit wire, is to use a splitter. Very good. So we're going to go get ourselves a splitter. So we split it, into 8 components. So we're going to have 8-bit wide, and also has a fan out of exactly 8. That way. And we can change the appearance. So we can make it look centered in this case. All right, so 8-bit to 8-bit, no problem with the width. And now we are just hooking up 1 bit to 1 LED. Now normally 1 LED has 2 terminals. One is the positive end and the other one is the negative end. But in a design like this, the negative end is implied. So that's why you only see 1 terminal per LED. All right. Cool. All right. And you can see these wires are blue. So if it is not light green or dark green or black in the case of a multi-bit wire, blue is telling you that we don't know what is on this wire. Why is that the case? Well, because the ROM module is not selected yet. Okay? So the ROM module has only 3 ports. The address port will let something outside of the ROM to specify which location do we want to retrieve. The D port will reflect the content at the location specified by the A port. But the select pin is also very important, because if the select pin is a 0, the ROM is pretending that it's not even there. It is not interpreting the A port, it's not driving the D port, it's just pretending that I'm not here. So in order for the ROM to do something, the select port has to be a 1. Okay? Now that is really useful when you have multiple ROM components in a design. But in this case, because we only have 1 ROM component, we can just say, we can make this always selected. In other words, it is always outputting something. Okay, but it's still complaining and saying, we don't know what to display. But that's because the A port is not connected to anything. So it is floating, and the module says, I don't know what you want me to display because nobody tells me which location I should output at the D port. So we'll take the output of the register, okay, which is here, and hook it up to the A port. And now we can see all the outputs are dark green, which means they are, every single wire going to an LED is now driven low. Okay, it's not floating, which blue is implying, but now it is actually driving low. Okay, are we good so far? So you go like, okay, so what does it do? What kind of pattern is it going to display when I clock this circuit? So we go to simulate, we say enable ticks, and you can see how this is like ticking by itself. You can also see how it is changing the location being addressed in the ROM, because that is reflected by the highlighting of the byte. But you can see that nothing too interesting is happening to the LED, because every location in the ROM is a 0. So they're all basically, every single frame is saying turn off all the LEDs. That is not very exciting. Okay? So what we'll do is going to try to make it more exciting. So how we want to make this more exciting is kind of up to you. I mean, do you guys want to, what kind of pattern do you want it to display? In other words, if you turn these 8 LEDs, like horizontally, and you slap that onto the hood of your car, how do you want that to display? Like, do you want to do the Cylon pattern, which is like, I think it's going like just center and then go wide and then back to center again? Or do you want to go for the kit, like Knight Rider pattern, which is scanning sideways? Pick one. Kit. Okay, very good. Okay, so we'll do the kit pattern, which is scanning sideways. So you kind of have to look at this with your head tilted to see it going sideways, but we'll just call it good enough. Okay. All right. So we'll basically say with this one, with the first location. So how you change the content of ROM or RAM is to right click on it, and then you go to edit content. It'll give you a very simplistic editor like this, where the italic number at the left edge of each line is telling you the beginning address of the first location of that row. Now, this is a very small ROM, so one row is more than enough to display the content of the entire thing. But the practical ROM is going to have more locations where you have multiple rows to show the content of the locations in the ROM. So the italic number all the way to the left is going to be useful in that case. But in this case, it's not very useful. Okay, so we'll just call this one as our leftmost LED, and we'll call this one our rightmost LED. So if I turn this into 8, 0, then it will have only this LED turned on and everything off. Is that making any sense? Because if I just want this one to be a 1 and everything else being 0, in hexadecimal digits, we would have 1, 0, 0, 0 as a binary pattern. And if you look up a lookup table for 1, 0, 0, 0 as 4 bits, it will be corresponding to 8 as a hexadecimal digit. Is that okay? So yeah, huh? 1, 0, 0, 0 is binary, but the hexadecimal digit corresponding to the 4-bit binary pattern is 8. Okay. And then the next one is 0, 0, 0, 0, which has just a single 0 as a hexadecimal digit corresponding to the 4-bit pattern of 0, 0, 0, 0. Is that good? Yep. Okay. All right, so we're going to do it like that. So you just type over, okay? You just type over. You don't have to press enter or anything. Just type 8, 0, and that's how you overwrite the content of one location. So the other part is going to be matching. So this is going to be 0, 1, where we only have one of the edge LEDs being on. So in the middle, we probably want these two to be symmetric. So now the question is, how many LEDs do we want to be on at the same time? So I'm just going to say 2, okay? 2 on to be at the same time. So we're going to have, let's see here. So we're going to have these two, those two, but then we have these two also on simultaneously. So we can have 3, or we can just have 1. So do you want to have just one? Do you want to have just one LED moving around, or I guess we can just go for 1 for now. Okay. So what would be the hexadecimal digits corresponding to only having this as a 1? So we have 0, 0, 0, 1 as a binary bit pattern, and that corresponds to just 1 in hexadecimal. The other 4 bits will still be 0, 0, 0, 0. Okay, so that would make this location a 1, 0, and this is going to be a 2, 0, and this is going to be a 4, 0. Why? Because after this LED, after it is 1, 0, 0, 0 like this, the next one is 0, 1, 0, 0. That bit pattern corresponds to hexadecimal digit 4. Then we have 0010, which corresponds to hexadecimal digit 2, and so on. Okay. And then on the other side, we'll have kind of the mirror image of all of this. So this would be 02, this would be 04, and this would be 08. Okay. So I claim that this is going to give us the Knight Rider kit, scanning motion, for the LED. So there's no need to save. Okay, so the save button is only useful if you want to save this pattern into a file. Okay, if you don't need to save it into a file, you don't need to click save. You can see the content are in the program into the ROM like almost right away. Is that okay? Okay. So we can just go ahead and close the window. And open, by the way, allows you to open a file. So after you save the content of ROM to a file, you can use open to reload the content of that ROM back into the ROM module. Okay. So right now we don't have to do a single thing. And every time you save the circuit, it will save the content of ROM. So there's no need to save the content of ROM separately. When you save the circuit includes the content of the programming of ROM. Okay. So now let's go ahead and see what happens when we enable ticking again. But it doesn't reverse. It only goes in one direction. So if you wanted to reverse, you probably want to have like multiple LEDs to be on at the same time. So we only can have like four steps going one way and 4 steps going the other way. Let's do that, because I don't like this when it's only going in one direction. Okay, so we'll stop it, and we'll see how fast you guys can do your hexadecimal digit manipulation. So what I want to do is to go from 1111 0000 to 0111 1000 00111100, and so on, and then have the pattern to go back. Okay. So how fast can you do your hexadecimal conversion? The first one is going to be F0. The second one is going to be 78. The third one is going to be a 3C. And then the fourth one is going to be a 1E. And then we'll have everything on the other side, which is 0F, and then scanning backwards. So we're going to have 1E again, and then 3C again, and then 7, 8 again. And then that will go back to the first one, because when you add 1 to 7, it goes back to 0. So this, I think, is the correct pattern. So let's go ahead and see whether this will give us the result that we want. Okay. So we go to simulate, and then go click on ticks enabled. Okay, so now does it go backwards? Yep. So now would be a good time to, also play the music of, Knight Rider, and also the swooshing sound of Knight Rider. I'm kind of surprised that so many of you actually know about Knight Rider, because it's a very ancient, show where today's technology actually has exceeded the science fiction. Does anyone know what I'm talking about? No one? Some of you? Okay. So I think that is truly interesting, because if you ask anyone back in those days, when Knight Rider first came out, and you ask, so how many years do you think it's going to take for this to become reality? People would just say that, oh, this is science fiction. It will never become true. Okay. And now you can actually talk to a Tesla and say, come pick me up, and it will. and the more interesting part is, a Tesla is not even, it doesn't even use gas. It's a full electric car. So Knight Rider could not even predict that cars would be fully electric. So So that's a very good example to show you how technology is progressing at a speed that is actually faster than science fiction predicts. So are we good so far with this example? Okay. Does it help illustrate what a ROM module is? Okay, this is a ROM module. So as far as you are concerned, a ROM module is really just like an array. It's just like an array because what you present to the A port is what you put inside the square brackets when you need to address the content of an array. What is going out of the ROM, which is the D port, is the content of one element in the array. Does that make sense? So when you make use of a ROM module, you're really it's just like addressing elements in an array. Are we good so far with this example?
Just not
Yep.
exactly how it controls the LEDs. I'm not exactly clear on how it controls the LEDs.
Oh, okay. So the way it controls an LED, or the 8 LEDs, is each bit of each location, each bit of the D port controls one LED. So you can see from the splitter, bit 0 controls the top LED, bit 1 controls the second to the top LED, and so on. So each location in the ROM has a particular pattern of ones and zeros. The ones would turn on an LED, and then the zeros would turn off an LED. And that's how the content of the ROM, like F0, would turn on the bottom 4 LEDs because bits 7, 6, 5, and 4 would be ones in that case.
Okay, so that's where, okay, because I thought that F0 just goes to the 0 pin.
Nope, F0 is broken up into 1, 1, 1, 1, 0, 0, 0, 0.
Okay.
Yep.
So what you had before you changed it so that it would go forwards and backwards?
Uh-huh.
Can you do that again just so I can see it again now that I've seen this?
Okay, sure. So the other pattern, which is not a kind of repeating pattern because it doesn't go back. Yep, so we can reprogram the ROM to do that. Uh-oh. No, we don't want to zero it. We could, because we are not actually keeping any specific content. So the other one is 80, 40, 20, 10, 08, 04, 02, and 01. And because only one bit out of the 8 is a 1 for every ROM location, and that's why you can see that each frame only has one LED turned on.
And then if you wanted to make it so that it was like it was doing before where it goes up and down,
Mm-hmm.
when you get to like the bottom very left one, would you make that 0, 1 and then so on and so forth?
Okay, so if you wanted to go back and forth, and this is the pattern that you want, then you need more ROM locations.
Okay.
Because we'll need 16 frames to complete the whole cycle, and with a 3-bit address port, we can only specify 8 frames, for the entire cycle. Yep. You go ahead and then Yep, go ahead.
If you have 10 bits coming out, how do you address those with hexadecimal? Doesn't that exceed how many?
You do it the same way. So what you do with 10 bits is you chop the 10 bits into chunks of 4 bits or less. But the key is to do it from right to left. So let me show you what I mean by that. So let's see, we go to mousepad. And of course it has to open it somewhere else. Not here. Not here. It opened it here. Okay. So we want this to go back to workspace 1. There we go. Okay. So let's say the 10 bits that we are talking about is A, B, C, D, E, F, G, okay, H, okay, there are 8 now, I, J, okay? So, so these are not hexadecimal digits. I'm just using these to represent the 10 digits, okay, the 10 binary digits. So the way you break it up into chunks of 4 is you start on the right-hand side. So these four will become one chunk of, 4 bits, and then you have the other four, which is this chunk here. Break it off into another chunk. So you do have, the AB being left alone by themselves, but you can sort of imagine that you have 0, 0 preceding the AB. So now you have quote unquote 3 chunks of 4 bits. And then you look up the lookup table, based on what A to J really are, then you can find the corresponding hexadecimal digits.
So you do a max of 3 as the leftmost.
Correct. So when you have 10 bits and you want to express it as a hexadecimal number, then you will need 3 digits to do it. That is correct. So go ahead.
What would dictate the speed?
The speed. So the speed of the animation has to do with the clock speed. So when you go to simulate, you can go to tick frequency, and you can make it like really fast. Okay, I can make this. So what you're seeing is really what we call the beat, of the whole thing, because it is refreshing the colors faster than the refresh rate of the monitor itself. So that's why we are not even seeing something that's continuous, because we are seeing the beat pattern.
So that's how you change it. You just change the Hurst.
Yeah, exactly. Well, that's one way to do it. So we can make it go to the more reasonable speed is probably be around 16, so it still be fast, but it will be sequential in that case. Like that. So it's still kind of cool. Any other questions about this particular design? No questions? So as far as we are concerned, this is just an array, okay? But the array has some kind of interesting attributes to it, because you can control the size or the width of the address port. That will do 2 things. It would actually change the size of the ROM, because the number of locations in the ROM is 2 to the power of the width of the A port. Okay. Number 2, the D port also has a programmable or changeable width, and that width changes how many bits we can store per location in the ROM. So there are 2 things we can adjust as far as a ROM module is concerned. Are we good so far with that? Yeah, with the discussion of ROM. Yes?
So if you change the D width to 10, would each of those display 3 digits then on the inside?
So if you change data bit width to 10, then this wire will be 10-bit wide. So as a 10-bit wide wire, I will now need to change the splitter. So if we only still have 8 LEDs, then we're going to have to lose 2 bits somehow. So 2 bits will not be connected to any one of the 8 LEDs.
But you had mentioned that if you want to display a 10-digit number, in hexadecimal you need 3 digits, right? So with it inside the ROM, would that update from 2 to 3
Yes, it would.
per spot?
Yep. So if I change the number of bit width, if I change the number of bits for the data bit, the ROM will now display, if I change it to 10, or if I change it to 9 to 12, then each location would use 3 digits in hexadecimal to display. Yes, so that would be correct. Yep. Any other questions about ROM? No questions? Okay. So now that we know what ROM is very closely related, but with some major differences. Okay, so we're going to add a new circuit, and we'll just say test RAM, because we're going to build a circuit to test a RAM component. So we drag a RAM component first and put it here. So right away you can recognize a few things about the RAM component. It has got an address port just like a ROM component, okay? And it does exactly the same thing. The address port is what we use to specify which location of the RAM we are trying to access, okay? And once again, the default width of the address port is 8, which means there are 2 to the power of 8, which is 256 locations in this particular component. So are we good so far? Because that is common, okay? That's the same with a ROM component. D port, kind of the same deal. The default is 8, but you can change it to anywhere between 1 and 32. So each location of RAM can also store the number of bits you can store in each location of RAM. It's also changeable or configurable by using the data bit width. Okay, so far they're almost exactly the same. But wait, there's one more similarity. It also has a select port. So once again, if the select port is a 0, this component will try to pretend that it's not even here. Okay, it would not interpret anything, it would not output anything. But if the select is a 1, then it would do things. Okay, so those three are common: A, select, and D. So those are the common ports between a RAM component and a ROM component that we just looked at. But it also has a few extra ports. Clear is kind of like reset for a register. If clear is a 1, then all the content of the RAM will be cleared all at once. Everything will become 0. Is that okay? So you can look at clear, CLR, as if it is just reset. It is the same thing as the port labeled 0 in the case of a register. Is that okay? Load is kind of interesting. Load is specifying the direction of the operation. If load is a 1, then it is a read operation, which means something outside of the RAM component is trying to read the content in this particular RAM component. Okay? So that means if load LD is a 0, it is a write operation. Something outside of the RAM component is going to specify and say, hey, RAM component, I want you to store this content into that location. Are we good so far? Okay. And here's a clock thing. The clock thing is totally missing in the ROM, but it is in a register. So it has the same purpose as the clock line or the clock port on the register. Upon a rising edge, that moment is when a RAM component, if it is configured for write operations, that's when it will sample the data port to change the address location in this content. Is that okay so far? Okay. So what we'll do next is we'll just play with this for a little bit. Okay. So what we'll do is we're gonna have pins to play with to connect to each port so that we can just kind of play with this and see what it does. Okay. And initially we'll use an A-bit output pin to connect to the D port, and then later on we'll find out that that's not always what we want to do, but we'll see. And then we'll have the clock. So everything is just going to be a pin in this case. I'm not going to use the clock signal because we don't need to have a repeating clock in this case. So everything is just a 1-bit input pin. And by the way, if you have questions about how a particular component works in Logisim, you can read the documentation, but then you can also experiment, just make a small circuit out of whatever component you're trying to learn and exercise it and then see if what you understand about the component is correct. Okay, so I highly recommend learning about components in that particular way. Okay. So the first thing we want to do is to, we can inject some content into the RAM. Okay, just like with ROM, you can right-click on the RAM component, and then click on Edit Content. Okay, so we'll go ahead and edit this particular location here. I'm just picking a location by random. So the first thing is, what location is that? So this time the italicized number all the way to the left-hand side becomes useful, because this tells you, the C0 here is telling you that's the address of the first byte of that entire row. So what it is saying, okay, I'm going to use a mouse pointer to help me identify the location. So this C0 here is saying this 00 is at location C0. So this is C1, C2, C3, C4, C5, C6. This would be location C7. Okay, So once again, okay, you can just type over the content. I'll just put this as E5, okay? For no particular reason, I just want to store hexadecimal E5 into that location. Are we good so far? Okay. So now the question is, how do I get E5 to display on the output pin here? Okay. So I'm going to move this one to here so that you can keep an eye on that content. So the question is, how do I do this? How do I get E5 to display as the output pin? Okay, first thing is we have to select. Now, the select is, you have to be careful with select, because the moment you enable, the moment you click on select, the component is going to wake up and it will try to interpret everything. In other words, that's the moment when it will say, which location do we want to go to? And are we reading, are we writing, and so on and so forth. So typically what most people would do is to set up everything else before they wake up the component and say, pay attention now. Okay, so you're correct. Eventually we want to specify a 1 for the select port, but we may not want to do that just yet until we got everything else set up. Yep. Okay, very good. So the A port is one of the things that we have to specify, and based on the location, which is C7, how do we specify these 8 bits? A C is 1100, and a 7 is 0111. Okay, and it will be handy to have a table if you want to bring a table to the next exam of the hexadecimal to binary conversion. I think that will come in handy. Okay, I can do all this really quickly because I've been doing this for decades, but you may not have the same experience as I do, so it's better to have a table, so this way you won't look up wrong, you won't remember incorrectly, you just look up a table. Okay. All right, so we got the address selected. Did I specify a read or write operation? I said I want to display the content of location C7 as the output, so that would be a read operation. Very good. So read operation says the load pin needs to be a 1. Okay. So if you're reading, it will automatically ignore the clock line, so the clock doesn't do a single thing. We definitely don't want clear to be a 1 because that would clear the content of the entire RAM, which kind of defeats the purpose of this exercise. So I think we got everything selected here. Or everything is configured correctly as far as the ports are concerned. So now we can turn on select, and it specifies some bits as the output. It highlights the location, which is great, but it also shows you the bits as the output pin. So we have E5 here. E is 1110, and then 5 is 0101. So we got the correct output. Okay, that's cool. All right, so now we know how to read a location from a RAM component. The next thing we want to do, guess what? We want to write, right? We want to overwrite a location in RAM. So to do that, okay, let me first turn off the select, because as we change all the other pins, it's good to tell the RAM component not to pay attention as we are fiddling with everything else. So to specify a new content, the D port is interesting because it is bidirectional. If you're reading, the D port is an output port. But when you're writing, the D port is an input port, so they can specify the new content to overwrite a location with. Okay? So you say, oh, that's not too big of a deal. All we need is a new input pin. Okay, so we specify a new input pin here that is 8-bit wide, and we'll change the heading so that it is consistent with the output pin. And we'll just hook up these two together. There's no problem with this, okay? There's no problem with connecting an input pin to an output pin, because an input pin is what allows you to configure the zeros and ones, okay? An output pin is just saying, okay, I can show you what is on this wire. but it's totally passive, right? So it's not a problem. Okay, so let's try to specify, okay, let's just try to specify the value of the byte right before the E5, okay? And we want it to be AB, okay? Just lowercase a, lowercase b. So how would we do that? The first thing is we need to compute the address. Well, if the address of the E5 is 11000111, the one right before, what would be what? I'm trying to specify the address of this location. This is already the address of the E5. So what do you think is one byte before that? Yep, change the least significant one to a 0. Okay, there we go. So we now got the right address. We want a write operation, which means the LD pin has to be a 0. So we got that. And we want to change that to AB instead of 00. A is 1010, and then B is 1011, like so. Now, can we double check and make sure this is actually AB in hexadecimal? The answer is yes, okay, but you have to kind of configure certain things first. Because if you poke the wire, it will show you some number, but none of that is in hexadecimal. 10101111 is just mirroring what we see as binary number on the pin, which is not very helpful, right? The second number after the slash is the base 10 signed interpretation of the bits. In other words, if I look at 10101011 as a signed 8-bit number, what is the base 10 representation of that value? Turns out to be -85. Well, it might be useful in some cases, but not in this case. So what we need to do in this case is to go to, I think it's under preferences. And under preferences, you can go to, I think it's layout, okay? So under layout, you have first radix when wire poked, and second. So instead of using a signed decimal, we can change it to hexadecimal. So this can be very handy because once we have changed that and we poke the wire again, it will now display, the first part is, I didn't change it, so it's still binary. But the second part is now in hexadecimal. So that can be very helpful when you're working with a processor to be able to poke a wire and then look at the content, not as base 2, but as base 16. Okay. So are there any questions at this point? No questions? Okay. So I think we got everything ready. So we'll now turn on the select. Okay. And you can see the chip, or the RAM component knows that we are addressing this particular location. That's good, right? But it's not changing yet. It's not changing yet because we are not seeing a rising edge at the clock yet. Okay? So just like a register, it doesn't change. It does not sample the D port to update a location until we see a rising edge at the clock. Okay? But that can be arranged easily. We just have to click on the clock pin once, and now we have a rising edge, and also at the same time, the location that we just addressed, it is still addressed, but now it is updated based on what the D port is experiencing. So are we good so far? Okay. So let's just say that, oh, this is good, right? We can read and write. Okay. So let's deselect it because we want to read the E5 again. Okay. So let's go back to the location of the E5. Okay. The address is just 1 byte after the one that we just addressed. Easy to adjust. We are reading, so LD needs to be a 1. And now we are ready to select the RAM component again. Click. Oh, we got a problem. We got a problem because, well, whenever you see a red wire in Logisim, that means we have a problem. To be more specific, when you see a red wire and you see an E, it usually means there's a disagreement of some kind. Now, what kind of disagreement do we have? How come some of the bits do not have an error and other bits have an error? Yep, go ahead. Because the D port of RAM is now an output, right? So it's trying to drive the wire, it's trying to drive the individual bits of the wire to whatever E5 is, which is 1110, 0101, okay? But the input pin is also trying to do the same thing. The input pin is trying to say, no, I want the second most significant bit to be a 0. The data port says, no, I want that to be a 1. Now there's a disagreement. That disagreement is also called a bus fight. Okay? So how do we resolve this problem? Well, what is the source of the problem? The source of the problem is the input pin is not supposed to have this connection at this point because we are not writing to the RAM component. We're only trying to read from the RAM component. Okay? So what we need in this case is to say, to fix this problem, we want this connection to be not always. Okay? Only sometimes we want to have this connection, but other times we don't want that connection. Okay? So whenever you have an application of we need to disconnect the driving of a wire sometimes, then you're probably looking into what we call a control buffer. Control buffer is here. It looks like this. And we're going to change the orientation just so that it follows the direction that we want. Okay. Okay, we'll put it right here. Okay. So a control buffer has 3 ports. Did we talk about the control buffer last time? I think we did. Okay. So this allows us to specify, oh, the input is going to be connecting to the input pin, okay, which means that part is always going to be there. The output, okay, we need to fix the width data bit to 8. There we go. And then the output is also going into here. But then we have a problem, okay? Well, that's because we haven't really specified whether it should be passing through the signal or it should be separating the signal. In other words, this gives us a chance to stop the input from being echoed on the output. So we know that this wire, okay, needs to go to, it is related to the load wire. But it's not exactly just the load wire. Because if I connect the load wire, which is this wire here, directly to the control port of the control buffer, then we're going to drive now, which is not what we want. We want exactly the opposite. So we just need a negation. So we go to negation, which is not, okay? And then we take the LD wire, and now we have the problem solved. Because whenever we are reading, whenever LD is a 1, we are disconnecting the input pin from the D port. And therefore, we don't have a fight. Is that making any sense? Because when you're reading, when LD is a 1, the D port is driving, but the input pins are driving as well. You cannot have 2 sources of driving the same wire because they can be driving in different directions. So this controlled buffer gives us a way to separate the connection from the input pin from this particular wire. On the other hand, yep.
Oh, I was gonna ask. You can finish your sentence. I was gonna ask why exactly you need a second in or a second D output when you actually do write.
When I do a write.
When you write to the RAM.
Okay, that's a good question. But this port here, this output port, you're basically asking why do we need an output port, right?
Well, second one for when you write.
This one?
Yeah.
Because this is representing something outside of the RAM component that is trying to specify the content to overwrite a location in RAM.
So you can use the output for that as well?
No, you cannot use this as an output. You can, because the output of D is not necessarily the same as what the other thing is trying to specify on the bus. So this will help us resolve the conflict. So if we are specifying a write operation, then the input pin does connect to the data port because in that case the data port is an input. But when we are reading, then the data port is going to be an output, then we're disconnecting the input pin, so we won't end up with two things trying to drive the same wire at the same time. Is that okay?
Yeah, that makes sense.
Okay. All right. So are we okay with the concept of a ROM and also the concept of a RAM? Okay. Any other questions about multiplexers and demultiplexers that we talked about last week? Okay, because they're basically just railroad switches that are directional. Okay, one has multiple in, one out, and the other ones have one in and multiple out. But in both cases, you need select bits. Okay, you need a select port to specify. Okay, I got one in, but which one should I connect it to the output? Or you have multiple in, and you only got one out. You have to select which one of the input pins connect to the one single output pin. Yep.
Are those completely directional? Like in this case, on that diagram, could you use a demultiplexer instead of that negation and control button?
You cannot use the multiplexer for this because a demultiplexer cannot deal with change of direction.
Okay.
Because in this case, the source of the problem has to do with D can change its direction.
Yeah, I wasn't sure if you could send and reverse through those.
Yeah, a multiplexer is only one directional. It's unidirectional. Yep. Okay. All right. So the next thing we're going to do is to actually go into the processor design now. So your lab is actually right on time, for this class. So to do that, I am going to open up the processor file, which is not there anymore because I just removed it, which is okay. I can show you guys how to get it back. Let's see. Nope, that one. There we go. All right, so this is part of your lab anyway. So your lab will give you these instructions. What you do is you go to the shared folder, and then when you get to the shared folder, you go to processor as a subfolder. And inside the processor subfolder, there are 3 files that you need to download. I would suggest that you download it onto a thumb drive. But if you don't, it's okay. You can re-download the 3 files every single time. Or you can put it into your own personal drive, so that way you know where to find it easily next time. So it's up to you. The 3 files that you need to download, one is alu.circ. The next one is processor 0003. You can do a control and then a click to select multiple files. And the last one is register bank, which is right here. So right click once you have all 3 files specified, click on download. It's going to zip it first, and then you will be downloading a zip file. And those files are supposed to be pretty small. I'm not sure why it takes so long to zip the files.
I had that problem this morning. It took like 10 minutes. Yeah.
10 minutes?
Like our Google Drive. It took a while to zip, and then downloading is instant.
Maybe the school is not paying much. So we're only getting the leftover processing power. Now this is really slow. It might be faster to download the files one at a time. Let's see if we can do that concurrently. Okay. Download. Okay, where is download? I don't see download.
I guess you have to cancel it.
Okay. Uh-oh. Specify the wrong name because I overwrote the name too. Okay, download again. Save file. And okay, that's one. processor 0003. And register bank. There we go. So when you're doing your lab, you probably want to do this. Also, just to download it separately. Just download all three to the same folder, okay? Because I think it is important that they're in the same folder. Okay. So now that I got all three downloaded, I can go back to Logisim. And go back to Logisim here. There we go. And then click on File, Open. I can go to Open Recent, or I can just go to Open. So specify the temp folder. And the one file that you should open is processor0003.circ. Okay, so do not open the other two, just open the processor file. So when you click Open, you might see some messages complaining where's the ALU, where's the regbank file, but probably not the case. And this is your processor, okay, or a small part of it. So let me zoom out a little bit so that we can kind of see the scale of the thing. This is your entire processor, which is actually very simple, okay? If you think about, this thing can actually run programs, okay? It's not really that big. So what we'll do next, is to kind of have a quick introduction to the various parts of the processor. Okay, so I'm going to identify the various parts. Now this part here, that is your RAM. Now RAM is not supposed to be truly a part of the processor, but a processor cannot do much without RAM. So that's why we have a RAM module kind of attached to the whole thing too. Is that okay? So technically speaking, this is not a part of the processor, but in order to make use of a processor, you need to have RAM connected to it. So that's why it's always there. Okay. And we also have ROM. Okay, if you go down here, we have one single ROM component here. And you can see, even without zooming in, I know you guys cannot actually see the digits on each row, but that's one location. You can see the ROM has a very wide, because each location has got, let me count, 1, 2, 3, 4, 5, 6, 7. It has got 7 hexadecimal digits, which means it has at least 25 bits, okay? So that at least 25 bits to one location of the ROM. You can also see a whole bunch of tunnels, okay? So let me just kind of zoom in a little bit. So if I zoom in just a little bit and pan down a little bit, you can see the output of the ROM goes through 2 splitters. It's a 2-stage splitting. It goes through one splitter where one of the split end, which is this one here, goes to another splitter to split into even smaller chunks. So there are tons of tunnels. Basically, each one is 1 or 2 bits most of the time of the output of the ROM. So now the question is, where are all of those things going? Well, the answer is all over the place. And that's why I use tunnels, because without using tunnels, it's going to look super duper messy. If you think this is messy, it will be like super messy without the use of tunnels. Okay. So we'll talk about what the ROM is doing here and why we have this huge mess of tunnels. But before we get there, we can look at this one as one component itself, but we can also look into it. This is the register bank, by the way. So when you look into a register bank, this is what it looks like inside a register bank. So this is simple enough that we can actually see what it is and kind of what it does. Okay. So let's go ahead and check this out first. We have register in. This is an 8-bit port, and we have register in select, and then this is in EN, or input enable. Okay. So we want to just look at how these things are wired. Do we know what A, B, C, and D's are? They're registers. Okay, so each one is a register. So this architecture has exactly 4 registers. Each register is 8-bit wide. Okay, but you can see that, hey, how come the D ports, they're all connected to the same wire which connects to register in? In other words, whatever is presented to register in, which is the A-bit input pin, it is presented to the D port of every single register. Then how do I know which one I'm supposed to update? Or do we have to update all 4 at the same time? What do you think? We have a decoder, which looks like a multiplexer, but it's not. So if you want to look at a decoder and say, how come it looks exactly like a multiplexer? Well, because it is a multiplexer with an input of constant 1. You can look at it that way. Okay? So you can look at a decoder like a multiplexer, except the input is always a 1. Is that okay? Well, then what does it do? I mean, then why do we have this decoder here? The select of the decoder goes to these 2 bits, which means only one of the outputs of the decoder can be a 1. Is that okay? If the select is 0, 0, then pin 0 of the output would be a 1. If input is 0, 1 for the select, then pin 1 would be a 1. Is that okay? It also has its enable pin. If the enable pin is a 0, then all pins are low. If the input pin or the input enable is a 1, then one and only one of the outputs would be a 1. Is that okay? That, in return, connects to the EN of the individual registers. So by changing these 2 bits of register input select, I can now specify which one of the 4 registers I want to update. Is that okay? But wait, if I want to update the register, I also need the clock. So let's look up the clock line here. This is the clock. So every single register has the clock line connected to the clock pin, which is visible from outside of the register bank. Is that okay? So the way you update one of the 4 registers would be, 1, you have to say input enable, it needs to be a 1. 2, you need to select one of the 4 registers by changing register input select. So it can go from 0, 0 to 1, 1. Okay? Third, you need to set up register input as the input pin. So you have to specify the new content of the selected register. And then last, you have to have a rising edge at the clock to actually update the register. Is that okay? Okay, that doesn't sound too bad, but why do we make this into a component on its own? Well, that's because we also need to specify the output. So let's focus on just register output 0. Okay? How is that connected to one of the 4 registers? In other words, you look at this output pin, and you look at this multiplexer. Oh, by the way, I just misspoke. A decoder is a demultiplexer with a constant of 1 as an input, not a multiplexer. Okay, but getting back to this multiplexer here. So how do I select which register is the output for register output 0? Well, you look at the multiplexer. The multiplexer has its own select pins. 0, 0 would be selecting register A. 0, 1 would select register B. 1, 0 would select register C. And then 1, 1 would select register D. In other words, by configuring register output 0 select, you can now select which one of the 4 registers will present its content as register output 0. Are we good over there? Okay. Then what about register output 1? Same deal, except it has its own select pins. So when you look at this entire thing, what exactly does it do? Well, it can serve, it has 3 main functions, okay? You can select one of the registers and say, I want to update you with this new content. You can also select one of the 4 registers and present the content of that register as register output 0. You can also select one of the 4 registers as register output 1. Next question, can we select the same register for all three operations. We want to update this register, and at the same time, we want the content of that register to show up as register output 0 as well as register output 1. The answer is yes. Okay, so it's flexible in that way. Then what about the other pins? What about these pins A, B, C, and D at the top of the design? It makes it possible for us to log the operation of the processor. When we get to debugging programs, you guys will thank me for having those around. Okay, but for now, they just look like, well, but why do we need those? Well, we'll just say this for debugging purposes. So are we good so far with the register bank itself? Yep.
Is having two register outs arbitrary? Why do you have two?
Oh, very good question. Okay, so why not just one, and why do we have two, and why not three, right? Why two? So the answer to that question is, if you go back to the main, okay, the second thing that we want to kind of focus on is this one here. This is the ALU, or this is the arithmetic and logic unit. Okay. We'll zoom into the arithmetic and logic unit, which is a little bit bigger and more complex compared to the register bank, but it will tell you why we have exactly two outputs of the register bank. Okay. We'll track down this guy. Okay. What is that? We saw that earlier today in class. It's the adder. Very good. So what are we adding? One thing comes from this demultiplexer. The other thing comes from the other demultiplexer. Is that okay? And how do we normally, okay, what do we use for adding? Registers. So for most arithmetic operations, you need two operands. And that's why we have two outputs from the register bank. Is we can say, oh, which register do we want as in 1, and which register do we want as in 2? That way we can specify the two operands for most arithmetic and logical operations. So that's a good question. I like that. But since we're here, we can also examine what kind of operations the ALU can do. Now remember, this is a very minimalist processor. Okay, it doesn't have any excess circuitry that is not necessary. Okay, so we can look through this and say, what can we do? We can add, we can subtract. Okay, we can do a right shift. Okay, this is the right shift operation, but we don't have a left shift. The reason why we don't have a left shift is if you add a number to itself, that is left shift. Okay, since we have another way to do it, we don't do it inside the circuitry, we do it by software. Okay, this is bitwise NOT, which means you're negating a whole bunch of bits at the same time. This is bitwise AND, and this is bitwise OR. So yes, I do remember we talked about NAND and how we can just use a NAND to replace every single logical operator. So by that standard, this is not as simple as it gets, because I do have these three separate logical gates, implemented individually, instead of having just a single NAND. And then we go through all the same math that we had before to use NANDs to specify all of the other operations. So for practical purposes, I do sometimes implement additional circuits, because otherwise it will take too many instructions to express something useful, and that makes the processor not very useful in the end. Okay. All right. But how do we specify which operation we want to perform? It looks like we can specify any one of these operations. The first thing is the demultiplexer will only send the input pin to the correct operation. By using OPSEL, or operation select, we can select only one of the operations to get the inputs. Are we good with that? But then we also use the same operation select to the multiplexer so that we pick up the output of the correct operation, and that becomes the output of the ALU. So that is how we specify one of the 6 operations inside the ALU, is by using OPSEL to connect to the demultiplexer for the inputs of the operation, and also using the same OPSEL to connect to select the output of the right operation to become the overall output of the ALU. Are we still doing okay so far with this? Now, this is all visible to you as well, okay? So studying for this class is now taking a weird turn in the sense that I'm not using text to describe the things that I'm teaching in class anymore, because the whole processor is, one, it's open sourced, and two, the whole thing is implemented in Logisim, so it is basically its own self-documentation. What I do in class is to explain the interaction between the components, and I'll do the explanation in like step-by-step, clock-by-clock, edge-by-edge fashion. So that is kind of like a weird change of how I explain things in this class, because I'm not using text to describe the operations anymore. Instead, the processor becomes a self-documenting entity. So that's why, at this point, today's lab is not very complicated. Okay, so between now and Wednesday, it will be helpful for you to review the operation of the individual components. What does a demultiplexer do? What does a multiplexer do? Okay, and then you go up and you say, what is a decoder? What does it do? What is a register? What does it do? What is a ROM? What does it do? What is a RAM? What does it do? Okay, so once you are familiar with each component and what it does, then when we talk about, oh, look at this thing here, it has got multiple things, then we can explain how the whole collection works as a single unit. Is that okay? So there's a lot of unspoken studying that you have to do by understanding the individual components of the processor. Okay? All right. So we're going to head out to the lab. The lab is fairly simple. I think most of you can get it done in like half an hour to 45 minutes.